Right now, 1.5 million kilometers from Earth, the James Webb Space Telescope is staring at worlds that should not exist. Planets where glass falls like rain at supersonic speeds. Surfaces so hot that rock becomes liquid oceans. Atmospheres collapsing in real time. And one world in particular has left scientists unable to explain what they are seeing. If you enjoy exploring the darkest corners of the universe, like and subscribe. We are about to visit 30 of the most extreme planets ever discovered. Prepare yourselves. We begin. James Webb pointed its instruments at a gas giant 690 light-years away and found something impossible. WASP 39b orbits its star every 4 days. The planet itself measures slightly larger than Saturn, but weighs far less. Scientists expected to find water vapor and maybe some carbon dioxide in its atmosphere. What came back changed everything we thought we knew about alien chemistry: sulfur dioxide. This compound only forms when ultraviolet light breaks apart molecules containing sulfur. On Earth, volcanoes release it during eruptions, but WASP 39b has no solid surface. No volcanoes exist there. The sulfur dioxide, detected by James Webb, formed through photochemistry, a process where starlight directly creates new molecules by smashing atoms together in the upper atmosphere. This marks the first confirmed detection of photochemistry on a planet outside our solar system. The implications shake the foundations of planetary science. For decades, scientists built models predicting which molecules should appear on different types of worlds. These models assumed chemistry worked the same everywhere. WASP 39b proves those assumptions wrong. Starlight can create compounds we never predicted. It transforms atmospheres in ways our equations missed entirely. The data revealed something stranger still. The sulfur dioxide concentration varies across different layers of the atmosphere. At higher altitudes, intense ultraviolet radiation creates it constantly. Deeper down, other chemical reactions destroy it just as fast. This creates a cycle, a churning system where molecules form and break apart in an endless loop. Temperature plays a brutal role here. The day side of WASP 39b reaches 900 degrees Celsius, hot enough to vaporize lead, hot enough to break molecular bonds that stay stable on Earth. In this inferno, chemistry operates under extreme conditions that laboratory experiments struggle to replicate. But temperature tells only part of the story. Pressure matters just as much. The atmosphere of WASP 39b presses down with crushing force. At certain depths, this pressure combined with heat creates states of matter that exist nowhere in our solar system. Gases behave like liquids. Distinct atmospheric layers blur together. The boundary between atmosphere and interior disappears into a gradual transition zone. Scientists analyzing the data found carbon dioxide levels far exceeding predictions. Methane appeared in concentrations that models said were impossible at these temperatures. Water vapor saturates the atmosphere at every altitude measured. Each new molecule detected raises fresh questions about how planets form and what processes shape their atmospheres over billions of years. The photochemistry discovery carries weight beyond one planet. If starlight creates unexpected molecules on WASP 39b, it likely happens on thousands of other worlds. Every exoplanet bathed in intense stellar radiation becomes a chemical laboratory conducting experiments nature never runs on Earth. We built our understanding of planetary atmospheres from studying 8 worlds in our solar system. The universe contains trillions of planets. WASP 39b reveals how little we actually know. What James Webb found next makes photochemistry look tame. Picture standing on a world where the sky itself wants to kill you. HD 189733. B appears beautiful from a distance. Deep blue coloring makes it resemble Earth in telescope images. This resemblance is a lie. The blue comes not from water but from silicate particles suspended in the atmosphere. These particles form when extreme heat vaporizes sand and glass. They hang in the air, reflecting light in wavelengths our eyes interpret as cobalt blue. Then the wind picks them up. Atmospheric measurements reveal wind speeds reaching 7,000 kilometers per hour. That's twice as fast as the speed of sound on Earth. These winds circle the entire planet in a never-ending jet stream that tears across hemispheres without stopping. The silicate particles caught in these winds become projectiles, microscopic shards of glass accelerated to supersonic velocities. It rains glass here, but the rain falls sideways. The temperature on HD 18973.3b hovers around 1000 degrees Celsius, hot enough to melt aluminum. At this temperature, silicon dioxide, the primary component of sand and glass, vaporizes into the atmosphere. As these vapor molecules rise and cool slightly, they condense back into solid particles. Tiny crystalline structures form. They grow. Eventually, they become heavy enough that gravity pulls them downward, except gravity barely gets a chance. The moment these glass particles form, hurricane-force winds grab them and hurl them horizontally across the planet. They never fall straight down. They shoot sideways at incomprehensible speeds, scouring anything in their path. The entire atmosphere acts as a planet-wide sandblaster operating continuously, without pause, without mercy. Scientists confirmed this through spectroscopic analysis. James Webb measured how light passes through the atmosphere at different angles. The data showed silicate particles scattered throughout the air in concentrations dense enough to create permanent haze. But the particles weren't stationary. They moved, fast. Doppler shift measurements revealed the wind speeds. As the planet orbits its star, light from the atmosphere shows a shift toward red on one side and blue on the other. This happens because wind carries particles toward us on one side of the planet and away from us on the other. The amount of shift directly correlates to velocity. The numbers came back extreme. HD 1897333. B orbits only 4.5 million kilometers from its star. For comparison, Earth orbits 150 million kilometers from its star. This proximity means the planet receives 30,000 times more radiation than Earth. Such intense heating creates massive temperature differences between the day side and night side. These temperature gradients drive the supersonic winds. The planet is tidally locked. One side permanently faces the star. The other side faces eternal darkness. The temperature difference between these hemispheres exceeds 700 degrees Celsius. Heat flows from hot to cold. On HD 1897333b, this flow becomes a violent atmospheric river that never stops moving. No spacecraft could survive here. The glass particles would shred any probe within seconds. The heat would melt metal components. The winds would tear apart anything we built. This world exists beyond our ability to visit or sample directly. We study it only through light, through the fingerprints molecules leave as starlight passes through alien skies. But compared to what comes next, sideways glass rain looks gentle. There are temperatures that break reality itself. Kelt 9b holds the record as the hottest planet ever discovered. The dayside reaches 4,300 degrees Celsius. This temperature exceeds the surface of many small stars. In fact, Kelt 9b burns hotter than 70% of all red dwarf stars in the galaxy. The planet itself radiates heat like a star. At this temperature, molecules cannot exist. Water vapor splits into hydrogen and oxygen atoms. Carbon dioxide shatters into separate carbon and oxygen. Even molecular hydrogen, the most stable molecule in the universe, tears apart into individual atoms. The atmosphere of Kelt 9b contains no molecules at all, only atomic gas. James Webb detected something even stranger: metals. Vaporized metals floating in the upper atmosphere. Iron, magnesium, sodium, and calcium exist as gases on Kelt 9b. On Earth, These elements form solid rocks and minerals. They build planets. On Kelt 9b, stellar radiation heats them beyond their boiling points. They evaporate. They drift through the sky as atomic vapors. The planet orbits its star every 1.5 days, 36 hours for a complete year. This places Kelt 9b closer to its star than Mercury orbits ours. The star itself burns blue-white, twice as hot as our star. It pours radiation onto the planet in amounts that defy comprehension. Scientists calculate that Kelt 9b receives energy equivalent to having 40,000 Earths worth of solar panels pointed at you, constantly. The radiation doesn't just heat the atmosphere, it ionizes atoms, stripping electrons away and creating plasma. Parts of the dayside atmosphere exist in a state somewhere between gas and star, but the planet is dying. Atmospheric escape measurements show Kelt 9b losing mass at an alarming rate. Every second, the planet sheds approximately 10 million kilograms of atmosphere into space. The intense heat gives atmospheric particles enough energy to reach escape velocity. They fly away, never to return. Over the planet's lifetime, it has lost a substantial fraction of its original atmosphere. Scientists estimate Kelt 9b once weighed significantly more than it does now. The star is slowly boiling it away. In another billion years, the planet might lose its entire gaseous envelope, leaving behind only a scorched rocky core, if a core even exists. Some researchers question whether Kelt 9b has a solid interior at all. The internal temperatures might be high enough to keep the entire planet in a semi-liquid state. Pressure from gravity holds it together, but beneath the atmosphere might lie a churning ocean of molten metallic hydrogen and helium, with no clear boundary to a solid core. The temperature gradient creates another bizarre effect. The dayside burns at over 4,000 degrees, while the nightside measures around 2,000 degrees. This 2,000-degree difference drives winds that circle the planet at supersonic speeds. These winds carry heat from day to night, but they cannot equalize the temperature. The star pours in too much energy too quickly. Observers on Earth have watched the brightness of Kelt 9b change over time. As the planet orbits, different parts face Earth. When the dayside points toward us, the planet shines brightly in infrared wavelengths. When it rotates away, the brightness drops. This variation allows scientists to map temperature across the surface. The maps reveal a hellscape beyond imagination. No part of Kelt 9b offers refuge from heat. No location provides shelter. The entire world exists as a furnace, a cautionary tale of what happens when planets orbit too close to their stars. Yet somewhere out there, a planet exists that makes this look cold. Imagine your entire year compressed into breakfast and lunch. Ultra-hot Jupiters complete full orbits around their stars in less than 1 day. Some finish a year in just 18 hours. These planets move so fast that observers can watch them complete multiple orbits in a single night of telescope time. The orbital velocities exceed 200 kilometers per second. Physics demands this speed. When a planet orbits extremely close to its star, gravity pulls harder. The planet must move faster to avoid falling inward. These worlds balance on a knife edge between staying in orbit and spiraling to their doom. One slight change in velocity, one gravitational nudge from a passing object, could send them plummeting into their stars. The tidal forces acting on these planets create strange effects. Gravity pulls harder on the near side than the far side. This difference stretches the planet into an elongated shape, slightly egg-like rather than perfectly spherical. The solid or liquid interior can't reshape itself fast enough to stay perfectly round as it whips around the star. Scientists call this tidal bulge. On Earth, tidal forces from the moon create ocean tides that rise and fall twice daily. On ultra-hot Jupiters, tidal forces distort the entire planet continuously. The bulge stays pointed toward the star, locked in place by gravitational interaction. This creates internal friction. As the planet rotates, its interior tries to move relative to the tidal bulge. Layers slide past each other, generating heat through friction. This tidal heating adds to the already extreme temperatures created by stellar radiation. The planets heat themselves through their own orbital mechanics. WASP 12b exemplifies this torture. It orbits so close to its star that tidal forces are literally tearing it apart. The planet is egg-shaped, stretched by gravity into a football-like form. Material from its outer layers streams away in twin plumes, one pointing toward the star and one pointing away. The star is eating it alive. Observations show a disk of planetary material spiraling into the star. Every second, WASP 12b loses mass as its outer atmosphere gets stripped away and consumed. Scientists predict the entire planet will be destroyed within 10 million years. We are watching planetary death in slow motion, but death takes different forms here. Some ultra-hot Jupiters don't spiral inward, they evaporate instead. The intense heat gives atmospheric particles enough energy to escape. The planet loses mass upward rather than inward. Either way, the outcome remains the same. These worlds cannot survive long-term in such extreme orbits. The discovery of ultra-hot Jupiters shocked astronomers. Planetary formation theory said they shouldn't exist. Gas giants form far from their stars where ice and gas are abundant. They need cold temperatures to accumulate massive atmospheres. Yet here they are, massive gas planets practically skimming the surface of their stars. This means they migrated. They formed farther out and then moved inward over millions of years. Something pushed or pulled them toward their stars. Interactions with other planets, gravitational effects from the protoplanetary disk, or encounters with passing stars could drive this migration. Each ultra-hot Jupiter represents a planetary system that went wrong. These are cautionary tales, examples of how gravity and orbital mechanics can doom entire worlds. They remind us that planetary orbits are not permanent. They can change, they can decay, and when they do, the results are catastrophic. But orbital decay isn't the strangest thing happening out there. On some planets, the atmosphere doesn't stay in the sky. HAT P7b shows weather patterns impossible on Earth. This planet experiences atmospheric collapse, a phenomenon where gases literally freeze out of the atmosphere and fall to the surface as solid or liquid precipitation. Then, when temperatures rise again, they evaporate back into gas. The entire atmosphere cycles between airborne and grounded states. This happens because of extreme temperature variations. The day side reaches 2,500 degrees Celsius. The night side drops to around 1,000 degrees. This 1,500-degree difference crosses critical thresholds for various atmospheric compounds. Compounds that exist as gases on the day side condense into liquids or solids on the night side. They fall like rain or snow, but this isn't water. This is molten rock, vaporized metals, and exotic compounds that have no equivalent on Earth. They condense out of the atmosphere, crash to the surface, and create temporary lakes or snowfields of materials that should never exist in liquid or solid form. Then the planet rotates. The nightside material moves into daylight. Temperature soars. The lakes boil away. The snowfields vaporize. Everything returns to the atmosphere as gas. The cycle repeats endlessly. Scientists detected this through light curve analysis. As HAT P7b orbits its star, the amount of light it reflects changes in unpredictable ways. Sometimes the planet appears bright. Other times, it dims. These variations don't match simple day-night patterns. They suggest something more complex happening in the atmosphere. Computer models revealed the answer. Clouds form and dissipate rapidly as atmospheric collapse occurs. When gases condense on the night side, they create clouds of condensed material. These clouds reflect starlight, making the planet appear brighter. When the clouds evaporate, brightness drops. The changing cloud cover creates the observed light variations. But HAT P7b shows another bizarre feature. The clouds are made of corundum. Corundum is aluminum oxide, the same mineral that forms rubies and sapphires on Earth. On HAT P7b, it exists as clouds. Tiny crystals of corundum form at high altitudes, where temperatures drop just enough for aluminum and oxygen to combine and condense. These crystal clouds drift through the upper atmosphere before falling to lower, hotter regions where they vaporize again. Imagine standing on the night side watching ruby snow fall from the sky, crystalline flakes of precious gemstone material tumbling down through alien darkness. Then sunrise comes. The ground heats. The rubies vaporize. They return to invisible gas. The surface clears until the next cycle begins. The atmospheric collapse affects wind patterns dramatically. When material condenses and falls on the night side, it removes mass from the atmosphere locally. This creates pressure differences. Gas flows from high-pressure regions on the day side to low-pressure regions on the night side. Massive atmospheric rivers develop, transporting heat and material across hemispheres. These winds reach several kilometers per second, fast enough to circle the entire planet in hours. They create chaotic turbulence as they collide with rising plumes of vaporized surface material on the day side. The atmosphere churns constantly, never reaching equilibrium. The planet cannot settle into stable weather patterns. Atmospheric collapse prevents it. Every location experiences rapid cycling between clear skies and dense clouds, between stable temperatures and wild fluctuations. If you could somehow survive there, the environment would change minute by minute in ways impossible to predict. No forecast model could predict this weather. The variables change too quickly. The physics operates too far from Earth-like conditions. This is weather beyond our ability to understand fully. And yet, atmospheric collapse isn't even the most extreme effect tidal locking creates. Half the planet never sees starlight, the other half never knows darkness. Tidal locking occurs when gravitational forces synchronize a planet's rotation with its orbit. One hemisphere faces the star perpetually, the other faces away forever. The same side always points toward the heat source. The same side always points toward cold space. Earth experiences day and night because it rotates. Every location gets sunshine and darkness in turn. Heat distributes somewhat evenly across the surface over time. Tidal-locked planets don't have this luxury. They're stuck, frozen in time. The temperature difference becomes extreme beyond anything Earth experiences. The day side of Kepler 10b reaches 2,600 degrees Celsius. The night side drops to near absolute zero in some models. This 2,600-degree gradient exists across a distance of only a few thousand kilometers, the width of the planet. No circulation system can balance this difference entirely. Atmospheric winds try. They transport heat from day to night constantly, but they cannot overcome the fundamental problem. One side receives all the stellar energy, the other receives none. This creates a terminator zone, the boundary between permanent day and permanent night. Along this twilight band, temperature exists in a narrow habitable range. Too far toward the day side, and heat becomes lethal. Too far toward the night side, and cold dominates. Only along the terminator could liquid water potentially exist, assuming the planet has water at all. Scientists speculate about life in terminator zones. If biology could develop on a tidally locked planet, it would likely concentrate in this narrow band. But the environment presents brutal challenges. The winds howling from day to night create permanent hurricanes along the terminator. Anything living there would face constant bombardment from supersonic atmospheric flows. The dayside presents different horrors. Under perpetual starlight, materials bake endlessly without relief. Rocks glow red-hot. Any volatiles evaporate immediately. The surface becomes desiccated, stripped of anything that can escape into the atmosphere. What remains is a scorched wasteland of refractory materials, elements and compounds with extremely high boiling points. The night side becomes equally hostile through opposite extremes. Without starlight, temperatures plummet. Any atmosphere present begins to freeze and fall to the surface. Atmospheric collapse accelerates on the night side of tidally locked planets because the cold never relents. Eventually, enough atmosphere might freeze out that the night side loses its gaseous envelope entirely, leaving only a thin frost of frozen nitrogen, oxygen, or whatever gases once filled the sky. This raises unsettling questions about atmospheric circulation. If the night side freezes out the atmosphere, where does the gas go? Does it all migrate to the day side? Do tidally locked planets develop wildly different atmospheric pressures on different hemispheres? Can atmosphere transport from day to night fast enough to prevent complete night side freezing? Current observations can't answer these questions fully. James Webb sees the combined light from entire planetary disks. It can't resolve surface details or map atmospheric density with sufficient precision yet. Scientists infer these effects from models and indirect measurements, but direct confirmation remains beyond our capabilities. What we do know is that tidal locking dramatically changes planetary environments. It creates worlds split into regions that bear no resemblance to each other. A single planet becomes two entirely different environments, separated by a narrow transition zone where both extremes meet and battle for dominance. Farther out, in deeper space, winds make even tidal locking look calm. HD 80606b experiences windstorms that would tear apart diamonds. This planet follows an extremely elliptical orbit. It swoops close to its star, then swings far away in a looping path that repeats every 111 days. During close approach, the temperature spikes from 800 degrees Celsius to 1200 degrees in just 6 hours. This rapid heating creates atmospheric chaos. The sudden temperature increase drives explosive convection. Hot gas expands violently, generating pressure waves that race around the planet. These pressure waves become supersonic shock waves. They travel faster than sound can propagate through the atmosphere. When they collide with cooler, denser gas, they create turbulence on a scale Earth never experiences. Wind speeds exceed 3 kilometers per second during these heating events. That's 10 times faster than the speed of sound on Earth. These winds carry enormous kinetic energy. Anything in their path would be pulverized by the sheer momentum of moving gas. But HD 80606b isn't alone in hosting extreme winds. Corot 7b generates winds through a different mechanism. This planet is tidally locked with one side perpetually facing its star. The day-night temperature difference reaches 2000 degrees Celsius. This gradient drives permanent wind circulation at speeds exceeding 2 kilometers per second. These winds never stop. They never vary much in strength. They flow continuously from dayside to nightside in an attempt to balance temperature, but they can never succeed. The dayside keeps receiving stellar energy. The nightside keeps radiating heat into space. The imbalance persists. The winds persist with it. The wind patterns create jet streams in upper atmospheres. On WASP 76b, spectroscopic measurements revealed a high-altitude jet stream moving at 14,000 kilometers per hour. This jet circles the entire planet, driven by the temperature differential between hemispheres. It carries vaporized iron from the dayside to the nightside. When iron vapor reaches the nightside, temperature drops below iron's condensation point. The vapor transforms into liquid droplets. It rains iron. Molten metal falls from the sky in sheets, driven by winds moving at supersonic speeds. This creates a one-way material transport system. Iron evaporates on the dayside, gets carried to the nightside by winds, condenses, and falls as rain, then presumably flows back to the dayside through subsurface channels or lower atmospheric currents to be evaporated again. The entire planet operates as a massive convection engine, processing metals through different states. The energy required to maintain these winds comes from the star. Stellar radiation heats the dayside. Hot gas expands and rises. Pressure differences develop. Gas flows from high to low pressure. This flow becomes wind. The process converts thermal energy into kinetic energy on a planetary scale. On Earth, our fastest winds barely exceed 500 kilometers per hour. Hurricane winds seem violent to us. Exoplanet winds would make hurricanes look like gentle breezes. The kinetic energy in these flows exceeds anything Earth's atmosphere can generate by factors of hundreds or thousands. What damage would such winds cause? They would scour surfaces clean of any loose material. They would erode rock through sheer abrasive force. They would make landing spacecraft impossible. Even in orbit, atmospheric drag from these high-velocity flows would destabilize satellites quickly. No life as we know it could survive in such conditions. Organisms need stable environments. They need protection from physical forces that would tear cells apart. Supersonic winds provide no such protection. They create conditions hostile to any chemistry complex enough to support biology. Yet these extreme winds reveal important truths about planetary atmospheres. They show how energy flows through atmospheric systems. They demonstrate the power of temperature gradients to drive motion. They prove that atmospheres are not static blankets but dynamic fluids responding to energy inputs. And the energy inputs keep getting more extreme. Some planets have atmospheres that would flatten you instantly. WASP 39b's carbon dioxide concentration exceeds Earth's by a factor of 10,000. This isn't just a thicker atmosphere. This is a fundamentally different type of atmospheric chemistry, where carbon dioxide dominates instead of nitrogen or hydrogen. The pressure at the cloud tops reaches several times Earth's sea level pressure. Deeper in the atmosphere, pressure builds to crushing levels. At depths equivalent to where jets fly on Earth, pressure on WASP 39b would exceed 1,000 times Earth atmospheric pressure. That's the pressure found at ocean depths of 10,000 meters. Under such pressure, gases behave strangely. They become so dense they blur the line between gas and liquid. Carbon dioxide enters what scientists call a supercritical state, where distinct phases disappear. It's not quite gas, not quite liquid. It exists as something in between with properties of both. This supercritical carbon dioxide creates unusual weather patterns. On Earth, clouds form when water vapor condenses into liquid droplets or ice crystals. On WASP 39b, supercritical carbon dioxide can't condense normally. Instead, it forms density variations, regions where the fluid becomes slightly more or less concentrated. These density variations affect how light passes through, creating cloud-like features without actual cloud formation. The crushing pressure affects chemical reactions dramatically. Some reactions that proceed slowly on Earth happen rapidly under high pressure. Other reactions that happen easily on Earth become impossible when pressure forces molecules too close together. The chemistry of WASP 39b operates under rules that laboratory chemists rarely encounter. Scientists also detected methane in WASP 39b's atmosphere. This surprised them. At the temperatures present on this planet, methane should break apart. Carbon and hydrogen should separate. The fact that methane persists suggests active chemical processes keep producing it faster than heat can destroy it. Something constantly regenerates the methane supply. Several theories attempt to explain this. Photochemistry might create methane through reactions driven by starlight. Vertical mixing might bring methane up from deeper, cooler layers where it can survive longer. Or some unknown chemical pathway might produce methane under the specific conditions present on WASP 39b. Whatever the source, the methane's presence reveals that high-pressure atmospheres can host active chemistry. They're not dead zones crushed into inertness. They're dynamic environments where molecules form, break apart, and recombine under conditions. Earth-based chemists struggle to replicate. The atmospheric structure differs from anything in our solar system. On Earth and other solar system planets, atmospheres show clear layering. Temperature decreases with altitude in the troposphere, then increases in the stratosphere, then decreases again in the mesosphere. This layering comes from how different atmospheric components absorb and emit radiation. WASP 39b shows different layering controlled by pressure rather than temperature. The atmosphere transitions gradually from low-density gas at high altitudes to supercritical fluid at mid-altitudes to potentially liquid or even solid phases at the deepest levels near the core. No clear boundaries exist, just smooth transitions between states of matter. If you could somehow descend through this atmosphere, the experience would be surreal. At first, you'd float through relatively normal-seeming gas. As you sank deeper, the air would become noticeably denser. Eventually, it would resist your motion like thick syrup. Deeper still, and you'd be swimming through fluid that flows like liquid but fills space like gas. Finally, before reaching any solid surface, you'd encounter conditions so extreme that your body and any vessel protecting you would be crushed into a compact mass. No spacecraft we can build would survive the descent. The pressure would exceed the crush depth of our deepest ocean submersibles. The heat would melt any known material. We can only study these atmospheres from a distance, using light to probe their composition and structure. But some atmospheres hold substances even stranger than supercritical carbon dioxide. Water vapor should not exist at 2000 degrees Celsius. Yet James Webb found it. K2-141b experiences surface temperatures that vaporize rock. Literally, the ground isn't solid. It's a magma ocean where stone melts and evaporates into the atmosphere. Nothing should survive in this environment, especially not water. Water molecules consist of hydrogen and oxygen bonded together. These bonds break at high temperatures. Above 1500 degrees Celsius, water vapor begins dissociating into separate hydrogen and oxygen atoms. At 2000 degrees, the process accelerates. Water molecules should not persist. Yet spectroscopic data clearly shows water vapor signatures in K2-141b's atmosphere. The absorption lines are unmistakable. Water is there. The question is how and why it survives. One possibility involves continuous production. Perhaps chemical reactions deep in the planet's interior keep generating new water molecules faster than heat destroys them. Hydrogen and oxygen might combine at certain pressure and temperature conditions, creating water that immediately rises into the atmosphere before breaking apart. Another explanation suggests the water exists in protected regions. Perhaps atmospheric circulation creates pockets or layers where temperature drops just enough for water to remain stable momentarily. The water would still face destruction, but it might persist long enough for detection before dissociating. A third, more disturbing option is that our understanding of water chemistry under extreme conditions is incomplete. Maybe water molecules can survive at higher temperatures than we calculated. Maybe pressure or other atmospheric factors stabilize the bonds in ways our models don't predict. WASP 121b presents a similar mystery. This ultra-hot Jupiter should have an atmosphere composed entirely of atoms, not molecules. Yet James Webb detected not just water but also molecular hydrogen, both existing at temperatures that should tear them apart. The findings challenge decades of atmospheric chemistry models. These models calculate bond energies, reaction rates, and dissociation temperatures based on laboratory experiments and quantum mechanics. The predictions are solid. Water should not survive in these conditions. The fact that it does means something important is missing from our understanding. Some scientists propose exotic chemistry driven by extreme ultraviolet radiation. Perhaps high-energy photons create transient molecules that exist for only microseconds before breaking apart. but constantly reform so quickly that steady-state concentrations build up despite rapid destruction. This would be chemistry in constant flux, molecules existing in dynamic equilibrium between formation and destruction. The water detection on these worlds matters beyond simple academic curiosity. Water is essential for life as we know it. Finding it in extreme environments expands the potential range of habitable conditions. If water persists at 2000 degrees, maybe biology could adapt to conditions we currently consider impossible. Not that anything could live on K2141b, the magma oceans alone would prevent that. But the principle extends to less extreme worlds. If chemistry behaves unexpectedly under harsh conditions, then our predictions about habitability might be too conservative. We might be overlooking potentially habitable worlds because we assume chemistry works in ways it actually doesn't. The presence of water on ultra-hot planets also affects planetary evolution. Water vapor in atmospheres affects how efficiently planets radiate heat into space. It influences cloud formation and atmospheric circulation patterns. If we incorrectly predict water content, we incorrectly model how these planets lose energy and evolve over time. Each new James Webb observation forces revisions to existing models. Scientists must update their equations, adjust their assumptions, and rebuild their understanding of exoplanet atmospheres from scratch. The universe keeps proving itself stranger than we imagined, and the strangeness only deepens when chemistry stops following any known rules at all. On TOI 270d, methane and carbon monoxide appear together in the same atmosphere. This should not happen. These two molecules cannot coexist in chemical equilibrium. They react with each other. Methane donates carbon and hydrogen. Carbon monoxide consumes oxygen. The two compounds should combine, creating carbon dioxide and hydrogen. The presence of both methane and carbon monoxide simultaneously violates basic chemical thermodynamics. Yet the James Webb data shows clear signatures of both molecules present at significant concentrations. The spectral lines don't lie. Both compounds exist in detectable amounts, despite the chemistry saying this is impossible. Scientists call this disequilibrium chemistry. It means the atmosphere exists far from chemical equilibrium. Reactions that should proceed to completion and eliminate one compound or another aren't happening fast enough. Something prevents the atmosphere from reaching its lowest energy state. Several mechanisms can drive disequilibrium. Photochemistry creates molecules through light-driven reactions that would never form in darkness. Vertical mixing brings up material from deep atmospheric layers before it can react with surface-level gases. Atmospheric circulation transports molecules faster than chemistry can act. But TOI 270d shows disequilibrium far beyond what these normal processes should produce. The methane and carbon monoxide concentrations are too high. The separation from equilibrium is too extreme. Something unusual is happening. One hypothesis suggests volcanic activity. If the planet has active volcanoes releasing both methane and carbon monoxide in large quantities, the input might overwhelm the atmospheric chemistry's ability to process these gases. The atmosphere would become a dumping ground for volcanic emissions, never reaching equilibrium because new material constantly floods in. Another possibility involves internal heat. If TOI 270d generates significant heat from radioactive decay or tidal flexing, this heat might drive chemical reactions in the deep atmosphere that produce disequilibrium molecules. These molecules rise to observable altitudes before they can react away. A more exotic explanation considers the possibility of biology. On Earth, life maintains atmospheric disequilibrium. Photosynthesis produces oxygen. Bacterial metabolism creates methane. These gases coexist in Earth's atmosphere only because life constantly regenerates them. Without life, Earth's atmosphere would reach equilibrium with oxygen and methane reacting away. Could biology on TOI 270d be producing methane and carbon monoxide? The planet orbits in what scientists call the habitable zone, the distance from its star where liquid water could exist. Temperatures might allow for life, at least in theory, but claiming biology based on atmospheric chemistry alone is premature. Too many abiotic processes can create disequilibrium. We need more evidence before suggesting life exists there. Scientists remain cautiously excited but skeptical. Other planets show different chemical impossibilities. WASP 76b has iron gas and titanium oxide in its upper atmosphere at the same time. These compounds should react immediately, forming iron titanate and removing both from the gas phase. Yet both persist, detected clearly through spectroscopy. GJ 1214b presents another puzzle. This planet shows evidence of hydrocarbon chemistry that makes no sense given the temperature and pressure conditions. Complex organic molecules appear when simpler compounds should dominate. The chemistry suggests pathways Earth-based models don't predict. Each impossible chemistry detection forces scientists to reconsider what they think they know. Chemistry doesn't actually break down on these planets. The laws of physics still hold, but the conditions are so extreme and so different from anything we can create in laboratories that our predictions fail. We built our understanding of chemistry from studying Earth-like conditions, temperatures around room temperature, pressures around 1 atmosphere. These are the conditions where most chemistry happens in our daily lives and in research labs. When we try to extend that knowledge to temperatures of thousands of degrees and pressures thousands of times higher, our models lose accuracy. The universe is conducting chemistry experiments we cannot replicate. These planets serve as natural laboratories exploring parameter space far beyond our experimental capabilities. The molecules they produce and maintain reveal gaps in our theoretical framework. What looks impossible to us is simply physics we don't yet understand fully. Each detection of unexpected chemistry is an opportunity to learn, to refine our models, to expand our knowledge of how matter behaves under extreme conditions. And some of those extreme conditions involve clouds made of things that have no business floating in the air. Picture clouds made of liquid iron drifting through alien skies. WASP 76b creates weather patterns that make Earth's storms look mundane. The dayside heats to 2,400 degrees Celsius. Hot enough to vaporize iron, solid metal becomes gas, rising into the atmosphere like water vapor on Earth. But iron vapor cannot stay gaseous when it drifts to cooler regions. The planet's rotation carries the vaporized iron from day to night. As it crosses the terminator into darkness, temperature drops. The iron vapor condenses into liquid droplets. Clouds form, clouds of molten metal suspended in the air. These aren't metaphorical clouds. They're actual clouds, matching the definition perfectly. Small droplets of a substance dispersed through a gas, held aloft by atmospheric currents. Except the droplets are molten iron at 1,600 degrees Celsius, and they fall as rain. Imagine standing on the night side watching the sky darken with metallic clouds. Rust-red formations drift overhead. Then the rain begins. Droplets of liquid iron plummet downward, glowing orange from internal heat. They hit the surface and splash, creating pools of molten metal that slowly cool and solidify. But the iron doesn't stay on the night side. Subsurface flows, or lower atmospheric currents, carry it back toward the day side. Temperature rises. The solid iron melts, then vaporizes. It rises back into the atmosphere to begin the cycle again. The planet operates as a massive iron circulation system. James Webb detected this through high-resolution spectroscopy. By observing the planet at different orbital positions, scientists measured how iron signatures varied. On the day side, iron existed as gas. On the night side, the gaseous iron signature weakened or disappeared, replaced by evidence of condensed particles. The condensed particles scatter light differently than gas. This scattering creates detectable changes in the planet's spectrum. Scientists can literally watch the iron transition from gas to liquid and back again as the planet rotates. WASP 76b isn't unique. Kepler 7b shows evidence of clouds containing magnesium and silicate particles. These clouds form at high altitudes, where temperature drops just enough for these compounds to condense. They create a reflective haze that makes the planet appear brighter than expected. The clouds affect planetary energy balance significantly. Reflective clouds bounce some stellar radiation back into space before it can heat the planet. This cooling effect can lower temperatures by hundreds of degrees in clouded regions. The planet's thermal structure depends heavily on where clouds form and how much area they cover. But clouds on exoplanets behave unpredictably. On Earth, cloud formation depends mostly on temperature and humidity. Water evaporates, rises, cools, condenses. The process is relatively straightforward. On exoplanets, dozens of different compounds can condense. Each one condenses at different temperatures and pressures. Each creates different cloud properties. Titanium oxide clouds form on some ultra-hot Jupiters. These clouds absorb stellar radiation strongly, heating the atmosphere from within. This creates temperature inversions where upper atmosphere becomes hotter than lower levels. On Earth, temperature normally decreases with altitude. Temperature inversions flip this pattern. The inversions affect how heat escapes. Normally, hot surfaces radiate infrared light upward through the atmosphere into space. When upper atmosphere is hotter than lower levels, radiation flows the wrong direction. Heat becomes trapped. The planet's ability to cool itself decreases. This creates runaway heating scenarios. More stellar radiation gets absorbed. Temperature rises. More titanium oxide vaporizes and forms clouds. More radiation gets absorbed. The cycle accelerates until some limit is reached, possibly when stellar radiation starts stripping away the atmosphere entirely. Metal clouds also affect atmospheric chemistry. Iron in the atmosphere can react with other elements, creating iron compounds that wouldn't form otherwise. These compounds then participate in further reactions, creating chemistry that depends on the presence of vaporized metals. Scientists studying Earth's atmosphere never needed to consider clouds made of metals. Our planet stays too cool for that. But the universe contains countless planets where metal clouds are normal weather. Understanding exoplanet atmospheres requires thinking beyond water and ice, beyond nitrogen and oxygen. It requires embracing chemistry that seems exotic by Earth standards, but is commonplace elsewhere. Yet some planets take atmospheric loss beyond simple evaporation. Every second, GJ 3470b loses 10,000 tons of atmosphere into space. This isn't geological timescale change. This is real-time planetary destruction observable during a single night of telescope time. The planet orbits a red dwarf star at a distance that subjects it to intense ultraviolet radiation. This radiation heats the upper atmosphere to extreme temperatures, giving atmospheric particles enough energy to escape gravity entirely. The escaping atmosphere forms a massive tail behind the planet, similar to a comet, except comets release ice and dust. GJ 3470b releases hydrogen and helium, the primary components of its atmosphere. The tail extends for millions of kilometers, a visible scar showing the planet slowly bleeding to death. Scientists detected this using transit spectroscopy. As GJ 3470b passes in front of its star, some starlight filters through the planet's atmosphere before reaching Earth. The escaping atmospheric tail extends far beyond the planet's solid body. This creates a much larger absorption signature than the planet's size alone would suggest. By measuring how much starlight the tail blocks, scientists calculate the mass loss rate. The numbers are staggering. At current rates, GJ 3470b will lose a significant fraction of its total atmosphere within 100 million years. The planet is actively shrinking. This raises questions about planetary populations. We observe many small planets orbiting close to their stars. Did these planets start larger? Did atmospheric escape reduce them to their current size? Are we seeing the remnants of once massive gas planets that lost everything except their rocky cores? Evidence suggests yes. Statistical analysis of exoplanet populations reveals a gap in the size distribution. Very few planets exist with radii between 1.5 and 2 Earth radii. Below this range, rocky planets dominate. Above it, gas-rich planets are common. The gap suggests atmospheric escape removes intermediate-sized planets, transforming them into smaller, rocky worlds. HD 209458b provides more evidence. This planet shows severe atmospheric escape, driven by its proximity to its star. Observations detected hydrogen, carbon, and oxygen streaming away from the planet at speeds of 35 kilometers per second, fast enough to escape the planet's gravity completely. The escaping material doesn't just drift away, it forms extended structures shaped by the planet's magnetic field and the stellar wind. The interaction creates bow shocks and magnetospheric structures visible in ultraviolet light. The planet carves a channel through its star's outer atmosphere as it orbits. But atmospheric escape affects planets differently depending on their composition. Gas giants can afford to lose tremendous amounts of atmosphere because they started with such massive envelopes. Rocky planets have thin atmospheres to begin with. Any significant loss can strip them bare completely. Kepler 444 hosts a system of 5 rocky planets orbiting extremely close to their star. These planets likely had atmospheres when they formed. The star's radiation has stripped those atmospheres away entirely. Now, they orbit as barren rocks, scorched by radiation with no gaseous blanket for protection. This atmospheric stripping has profound implications for habitability. A planet might form with all the right ingredients for life: liquid water, organic compounds, stable temperatures. But if it orbits too close to its star, radiation strips away the atmosphere. The water evaporates into space. Surface conditions become hostile. Even planets in nominal habitable zones face risk. Red dwarf stars, the most common type of star in the galaxy, emit powerful stellar flares. These flares release bursts of ultraviolet and X-ray radiation that can strip atmospheres from nearby planets. A planet might orbit at the perfect distance for liquid water, but still lose its atmosphere to stellar activity. The timescales matter too. Young stars are more active than old stars. A planet might endure billions of years of intense radiation during its star's youth before conditions calm down. Could life survive through such punishment? Or does atmospheric stripping eliminate habitability before biology can gain a foothold? These questions remain open, but the observations are clear. Atmospheric escape is common. Many planets lose significant portions of their atmospheres over time. Some might lose everything, and the consequences of that loss grow more severe when you realize what else escapes besides gas. There is no place to land on K2 141b because there is no solid surface. The entire dayside exists as an ocean of molten rock, not occasional lava flows like on Earth, not volcanic regions scattered across a solid crust. The entire hemisphere is liquid, magma 100 kilometers deep covering everything. Temperature reaches 3,000 degrees Celsius. Rock vaporizes directly from the ocean surface into the atmosphere. This isn't speculation. Infrared measurements from James Webb confirm surface temperatures high enough to melt any known mineral. The planet emits thermal radiation consistent with a glowing hot liquid surface. No solid ground exists beneath the magma, just deeper, hotter layers of molten material extending down to the core. The lava ocean circulates. Heat drives convection currents. Hot magma rises from the depths. Cooler magma at the surface sinks. The entire ocean churns constantly, mixing material from top to bottom. Anything that somehow fell into this ocean would be pulled down, melted, and incorporated into the circulation. Waves cross the magma ocean's surface. Not water waves, waves of molten rock driven by atmospheric winds. These waves reach heights of several meters. They crash and reform continuously. The violence of liquid rock in motion defies comprehension. On the night side, conditions differ but remain hostile. Temperature drops to 1,700 degrees Celsius, still hot enough to melt most rocks, but cool enough for some materials to solidify. A thin, brittle crust might form. Then the planet's rotation carries it back toward dayside. Heat increases. The crust melts again. The atmosphere of K2-141b consists largely of vaporized rock. Sodium, silicon, oxygen, and other elements evaporate from the magma ocean and drift upward. These vapors condense into clouds at higher, cooler altitudes. Then gravity pulls them back down as precipitation. Rock rain falls onto a rock ocean in an endless cycle. This creates weather patterns impossible on Earth. Instead of water cycling between ocean and sky, rock cycles through the same process: evaporation, condensation, precipitation. The same physics applies, only the material changes. Scientists studying K2-141b have detected wind patterns carrying rock vapor from dayside to nightside. The vapor travels through the atmosphere, carried by supersonic winds. When it reaches the nightside where temperature drops, it condenses. Rock snow falls onto the surface. Then, subsurface flows carry the solidified rock back toward the dayside, where it melts and evaporates again. The planet operates as a heat engine. Stellar radiation provides energy. The temperature difference between day and night drives atmospheric circulation. Magma ocean convection transports heat internally. Everything moves. Nothing stays still. The entire world exists in constant, violent motion. No life could exist in these conditions. The temperature alone prevents it. But the chemical environment is also wrong. Life requires complex molecules. Complex molecules break apart at temperatures above a few hundred degrees. K2-141b maintains temperatures measured in thousands of degrees. No organic chemistry survives. No biology is possible. Yet K2-141b isn't the only lava ocean planet discovered. Koro T7b shows similar surface conditions. 55 Cancri E might have a lava ocean on its dayside. These worlds represent a class of planets so hot that their surfaces exist in a molten state permanently. They challenge our understanding of planetary interiors. On Earth, we study the interior by examining lava from volcanic eruption. This lava comes from deep underground, bringing samples of the mantle to the surface. On lava ocean planets, the entire surface is the interior. There's no crust, no separate mantle and core layers. Just a gradual transition from liquid surface to denser liquid depths. This affects how we model these planets. Normal planetary models assume distinct layers with different compositions and states. Lava ocean planets don't have those distinct layers. They require different modeling approaches that account for continuous transitions rather than sharp boundaries. The existence of lava oceans also tells us about planet formation. These worlds formed from the same protoplanetary disk materials as Earth, yet they ended up completely different. Their close proximity to their stars determined their fate. A planet's final condition depends critically on where it forms and where it migrates to, and migration can create even stranger surface features than permanent magma. The sky on HD 209458b glows yellow from sodium gas. Sodium, the metal that forms table salt when combined with chlorine, exists as a vapor in this planet's upper atmosphere. Normally, sodium stays locked in rocks and minerals. Temperature and energy requirements keep it solid or dissolved in liquids. But at 1100 degrees Celsius, sodium vaporizes and rises into the air. James Webb detected sodium through absorption spectroscopy. Sodium atoms absorb light at very specific wavelengths, creating distinct dark lines in the spectrum. These lines are unmistakable. No other element creates the same pattern. When starlight passes through the atmosphere during a transit, sodium atoms remove their characteristic wavelengths from the light. The amount of absorption reveals sodium concentration. HDB shows sodium levels far exceeding expectations. The upper atmosphere contains enough gaseous sodium to significantly affect how the planet looks. If you could somehow view it from nearby, the atmospheric glow would have a yellowish tint from sodium emission. Potassium joins sodium in the atmosphere. This metal vaporizes at similar temperatures. Together, sodium and potassium create a metallic haze in the upper atmosphere. These alkali metals are highly reactive. They interact with other atmospheric compounds, driving chemistry that Earth's atmosphere never experiences. The presence of gaseous metals affects atmospheric structure profoundly. Sodium and potassium absorb stellar radiation efficiently. This absorption heats the upper atmosphere from within. Temperature increases with altitude instead of decreasing, as it does on Earth. The atmosphere develops a temperature inversion. This inversion traps heat. The hot upper layers act as a blanket, preventing cooler lower atmosphere from radiating energy into space efficiently. The planet's internal temperature rises. This drives more metals into vapor form. More absorption occurs. More heating results. The process reinforces itself. Other planets show different metal signatures. WASP 9-6b has strong sodium lines. HAT P 1b shows both sodium and potassium. These detections reveal that vaporized metals are common in hot exoplanet atmospheres. What seems exotic by Earth standards is routine across the galaxy. The metals don't just float passively. They participate in atmospheric chemistry. Sodium can react with oxygen to form sodium oxide. It reacts with sulfur compounds. It can even react with water vapor, though water is scarce in these hot atmospheres. Each reaction changes atmospheric composition and affects what other reactions can occur. Scientists studying these atmospheres must account for metal chemistry in their models. Standard atmospheric models, developed for Earth-like planets, assume nitrogen and oxygen chemistry. Adding sodium, potassium, iron, and other metals requires completely different chemical pathways and reaction networks. This complicates efforts to understand atmospheric evolution. As planets age and their atmospheres change, metal content varies. Young hot planets might have more gaseous metals as outgassing from recent formation continues. Older planets might have depleted their metal vapor supplies. Age affects atmospheric composition in ways we're only beginning to map. The metal content also affects observability. Sodium and potassium create strong spectral features. This makes planets with metallic atmospheres easier to characterize than planets with bland atmospheric compositions. Scientists preferentially study planets with strong metal signatures because the data quality is better. This creates a selection bias in our sample of studied exoplanets. We know a lot about planets with metal-rich atmospheres. We know less about planets with clearer atmospheres, or atmospheres dominated by molecules that don't absorb strongly at the wavelengths we can easily observe. Our understanding of exoplanet diversity remains incomplete because of these observational limitations. Future missions might address this. Better telescopes with broader wavelength coverage and higher sensitivity could detect fainter atmospheric features. This would reveal planets currently hiding in our data. But for now, metallic atmospheres dominate our observations because they scream their presence in the data. And some planets lost their atmospheres so thoroughly that they scream in a different way entirely, through silence. Kepler 10b has no atmosphere whatsoever. This rocky planet orbits so close to its star that radiation has stripped away every last gas molecule. No protective blanket exists. The naked surface faces stellar wind and radiation directly. Temperature reaches 2600 degrees Celsius. Any atmosphere that tries to form evaporates immediately. Scientists confirm the lack of atmosphere through transit observations. When Kepler 10b passes in front of its star, it blocks a precise amount of light. That amount corresponds exactly to the planet's physical size. There's no extended atmosphere creating extra absorption, no high-altitude haze scattering light, nothing, just bare rock. This makes Kepler 10b one of the most hostile environments imaginable. Without an atmosphere, there's no weather, no winds, no clouds, no precipitation, just a scorched rock in space, bathed in radiation with no protection. The surface material itself becomes questionable. At 2600 degrees, most minerals melt or vaporize. The surface might be partially molten, or it might consist of refractory materials, compounds with extremely high melting points that can survive these temperatures in solid form. Tungsten, osmium, carbon in the form of graphite, these might constitute the surface. But even refractory materials face destruction. Stellar radiation doesn't just heat surfaces, it ionizes atoms, stripping electrons away. It breaks chemical bonds. It causes materials to photodissociate and evaporate atom by atom even below their normal boiling points. The surface of Kepler 10b slowly ablates away under constant radiation bombardment. Without an atmosphere, temperature varies wildly between day and night. The day side bakes under direct starlight. The night side radiates heat into space with nothing to slow the loss. Temperature differences might exceed 2000 degrees across the terminator zone. Materials expand and contract with these temperature swings, creating stress fractures that could shatter surface rocks repeatedly. This thermal cycling creates a unique form of erosion. Rocks crack from temperature stress. The cracks propagate. Eventually, rocks break apart into smaller fragments. But with no atmosphere, there's no wind to move these fragments. They stay where they are unless some other force acts on them. Micrometeorite impacts provide that force. Without an atmosphere to burn up incoming debris, every particle strikes the surface at full velocity. These impacts sandblast the surface continuously, grinding rocks into finer and finer powder over geological timescales. The powder might not stay on the surface. Solar radiation pressure can push small particles, especially if they're electrically charged. Over time, the finest dust might escape the planet entirely, creating a tenuous cloud of particles extending beyond the planet's orbit. The planet slowly disintegrates grain by grain. Other airless exoplanets show similar characteristics. Corot 7b likely has little to no atmosphere. Kepler 78b orbits even closer to its star and shows no atmospheric signature. These worlds represent planetary evolution taken to an extreme endpoint. They started with atmospheres. Radiation stripped them away. Now they orbit as bare remnants. The lack of atmosphere eliminates any possibility of habitability. Life, as we know it, requires air for protection, for temperature regulation, for chemical cycling. Without atmosphere, none of these functions exist. The surface connects directly to space. No biosphere could establish itself. Yet these barren worlds serve important scientific purposes. They provide laboratories for studying extreme surface conditions. The materials that survive on airless exoplanets tell us about the most refractory compounds in the universe. The erosion processes operating there reveal how matter behaves under constant radiation stress. They also serve as warnings. Earth has an atmosphere now, but the processes stripping atmospheres from exoplanets could act on Earth given the right conditions. If our star became more active, if Earth somehow migrated closer to it, atmospheric escape could begin here too. These distant stripped planets show Earth's potential fate under sufficiently hostile conditions. And when gravity itself becomes hostile, planets face torture of a different kind entirely. TOI 849b has gravity 4 times stronger than Earth. Walk on this planet and your weight quadruples. Your legs strain to move. Your heart works 4 times harder to pump blood upward. Standing requires constant muscular effort. Moving feels like wading through thick liquid. This is what super-Earth gravity does to anything on the surface. The planet itself weighs 40 times more than Earth, despite having a radius only 3.5 times larger. That mass packs into a relatively small volume, creating intense gravitational fields. Everything pulls downward with crushing force. This gravity affects atmospheric structure dramatically. On Earth, atmospheric pressure decreases smoothly with altitude. On super-Earths, the decrease is much steeper. The atmosphere compresses into a thin layer hugging the surface. Above that layer, density drops rapidly. The atmosphere has nowhere else to go. Gravity holds it tight against the ground. The surface pressure reaches extreme levels. On TOI 849b, scientists estimate surface pressure could exceed 100 times Earth's sea level pressure. That's the pressure found deep in Earth's oceans. But this pressure exists at the surface, pressing down on everything there. Under such pressure, matter behaves strangely. Gases compress into liquid-like densities. Distinctions between atmospheric layers blur. The lower atmosphere becomes more like an ocean of dense gas than recognizable air. Anything existing at the surface must withstand constant crushing force. The high gravity also affects atmospheric escape. On Earth, the escape velocity is 11 kilometers per second. On TOI 849b, it's approximately 40 kilometers per second. Atmospheric particles need far more energy to escape. This makes atmospheric retention extremely efficient. Super-Earths hold onto their atmospheres tenaciously, but retention creates problems. With gravity preventing atmospheric escape, volatile compounds accumulate rather than dissipating. If volcanic activity releases toxic gases, those gases stay in the atmosphere indefinitely. They build up to dangerous levels. The atmosphere becomes a repository for every outgassing event in the planet's history. Scientists detected hydrogen and helium in TOI 849b's atmosphere, despite the planet's high temperature. Normally, these light elements escape easily from hot planets. But TOI 849b's gravity is too strong. Even hydrogen struggles to reach escape velocity. The planet retains elements it would otherwise lose. This affects planetary evolution. On Earth, light elements escaped early in our planet's history. This loss helped create our current atmospheric composition. On super-Earths, light elements stick around. The atmosphere retains its primordial composition longer. Chemical evolution proceeds differently when nothing can leave. The strong gravity also affects geological processes. Tectonic activity becomes harder to sustain. The weight of the crust presses down more forcefully. Mantle convection must overcome greater resistance. Volcanic eruptions need more pressure to force magma through the thick crust. Everything moves more slowly or not at all. A super-Earth might develop a stagnant lid instead of active plate tectonics. The crust forms one solid shell that never breaks apart or recycles. No subduction occurs. No continental drift. The surface locks in place, geologically dead or sluggish at best. Without active geology, atmospheric recycling stops. On Earth, plate tectonics removes carbon dioxide from the air and stores it in rocks. This regulates climate over millions of years. Super-Earths lacking plate tectonics have no such regulation. Carbon dioxide and other gases accumulate unchecked. The combination of thick atmospheres and stagnant geology creates extreme greenhouse effects. Heat gets trapped efficiently. Surface temperatures rise far above what stellar radiation alone would cause. The planet bakes itself through its own atmospheric composition. TOI 849b shows another strange feature. Despite being a super-Earth, it has very little atmosphere relative to its size. Scientists think this planet might be an exposed planetary core. The original atmosphere got stripped away somehow, leaving only the dense metallic interior. What we see now is the naked heart of a former gas giant. This suggests super-Earths can form through different pathways. Some might be scaled-up rocky planets. Others might be stripped gas giant cores. Their high masses don't necessarily mean they all share similar compositions or formation histories. And when super-Earths orbit the wrong type of star, their problems multiply beyond simple gravity. LHS 3844b orbits a red dwarf star smaller and cooler than ours. This changes everything about how the planet works. Red dwarfs emit most of their energy in infrared rather than visible light. They burn at lower temperatures. They live for trillions of years instead of billions. And they bathe their planets in radiation spectrums nothing like what Earth receives. The infrared-heavy radiation affects atmospheric chemistry. Molecules absorb and emit infrared wavelengths differently than visible light. Chemical reactions driven by stellar energy proceed through different pathways. Photochemistry that works one way under yellow starlight works differently under red starlight. Red dwarfs also emit powerful flares. These stars have intense magnetic fields that twist and snap, releasing bursts of ultraviolet and X-ray radiation. A single flare can increase stellar brightness by factors of 10 or more. Planets orbiting red dwarfs get repeatedly blasted with radiation doses that would sterilize Earth's surface. LHS 3844b likely has no atmosphere, partly because of this flare activity. Every time the star flares, radiation strips away atmospheric gases. Over billions of years, the cumulative effect removes everything. The planet becomes bare rock, despite orbiting in a temperate zone where liquid water should be possible. The flares create another problem. They accelerate particles in the stellar wind. These particles strike planetary atmospheres at high velocities, physically sputtering atoms away through collision. This atmospheric sputtering supplements photochemical escape, doubling the loss rate. Red dwarf planets also face tidal locking more readily than planets around larger stars. The closer orbital distances and longer timescales involved mean gravitational forces have more time to synchronize rotation with orbit. Most planets in red dwarf habitable zones probably show the same face to their star perpetually. This creates the day-night temperature extreme problem discussed earlier. But on red dwarf planets, the temperature difference might be even more severe because the star's lower luminosity means less heat reaches the night side through atmospheric circulation. The night side becomes extremely cold while the day side moderates to potentially habitable temperatures. The habitable zone around red dwarfs sits close to the star. This proximity increases tidal forces and radiation exposure. Planets must balance in a narrow sweet spot where temperature allows liquid water but radiation doesn't strip the atmosphere. Few planets thread this needle successfully. Stellar activity varies dramatically among red dwarfs. Young red dwarfs are extremely active, flaring constantly and emitting high levels of ultraviolet radiation. Old red dwarfs calm down, flaring less frequently with lower energy releases. A planet's habitability might depend entirely on its star's age. If a planet can survive through its star's active youth, conditions might eventually settle into something more stable. But surviving for the first billion years presents enormous challenges. The planet needs a thick atmosphere to absorb radiation and a strong magnetic field to deflect charged particles. Without both, the surface remains hostile. LHS 3844b failed this survival test. James Webb observations show a bare rock with no protective atmosphere. The surface consists of dark volcanic rock baked by infrared radiation and blasted by stellar wind. Nothing shields it. Nothing moderates conditions. The planet exists as a warning of what happens when stellar activity wins. Yet red dwarfs are the most common stars in the galaxy. 70% of all stars are red dwarfs. If planets around them struggle with habitability, then the galaxy contains far fewer potentially habitable worlds than population statistics suggest. The sheer number of red dwarfs doesn't translate to abundant habitable planets if the stellar environment is too harsh. Understanding red dwarf planets matters enormously for astrobiology. These stars will outlive all others. In the far future, red dwarfs will be the only stars still burning. If life cannot survive on their planets, then life's cosmic future looks limited. But stellar radiation alone doesn't kill atmospheres. Sometimes stars destroy them through direct physical stripping. The star is physically blowing away the planet's atmosphere. HD 189733b doesn't just lose atmosphere through evaporation. The stellar wind, a stream of charged particles flowing outward from the star, hits the atmosphere with physical force. These particles collide with atmospheric molecules, transferring momentum and literally push gases into space. Think of it like sandblasting. Each particle impact removes a tiny amount of material. Billions of impacts per second add up. Over millions of years, the cumulative effect strips away substantial atmospheric mass. Scientists measured this through observations of escaping hydrogen. When the planet transits its star, some starlight passes through the extended hydrogen cloud surrounding the planet. This cloud extends far beyond the planet's solid body, stretching millions of kilometers into space. The hydrogen isn't bound to the planet anymore. It's leaving. The escape happens preferentially on the day side. Stellar wind hits the day side directly, creating maximum pressure. The night side receives less direct impact. This asymmetry creates a comet-like tail of escaping atmosphere streaming away from the star-facing side. Magnetic fields complicate the process. If a planet has a strong magnetic field, it can deflect some stellar wind particles. The field creates a protective bubble called a magnetosphere. Charged particles flow around this bubble rather than striking the atmosphere directly. Earth's magnetic field provides exactly this protection. But HD 189733b likely has a weak magnetic field or none at all. Gas giants don't generate strong magnetic fields as easily as rocky planets with metallic cores. Without magnetic protection, the atmosphere faces the stellar wind unshielded. The stellar wind varies in strength. When the star flares, wind intensity increases dramatically. Particles accelerate to higher velocities. The pressure on the atmosphere multiplies. During these flare events, atmospheric loss rates spike by factors of 10 or more. Scientists can measure stellar wind properties by observing how it affects the star's outer atmosphere. The wind carries away some of the star's own material. This creates spectral signatures revealing wind speed and density. By studying these signatures, researchers calculate the pressure the wind exerts on nearby planets. The calculations for HD 189733b show disturbing results. The planet loses atmosphere at a rate that will remove significant mass over its remaining lifetime. It won't lose everything. The planet is massive enough to retain most of its atmosphere through gravitational binding, but it will shrink measurably. Other planets face worse fates. Smaller planets with weaker gravity cannot hold atmosphere against intense stellar winds. They lose everything. The process transforms gas-rich planets into bare, rocky cores over hundreds of millions of years. The stellar wind stripping process depends heavily on orbital distance. Closer planets face stronger winds. The wind intensity decreases with the square of distance. A planet twice as far from its star receives 1/4 the wind pressure. This creates a sharp boundary beyond which stellar wind stripping becomes negligible. Most ultra-hot Jupiters orbit inside this boundary. They face maximum stellar wind exposure. Their atmospheres erode continuously. Some might be former super-Jupiters that lost significant mass to wind stripping, leaving behind the smaller gas giants we observe today. The composition of escaping material tells scientists about atmospheric structure. Light elements escape more easily than heavy ones. If observations show mostly hydrogen leaving, the atmosphere probably has a hydrogen-rich outer layer. If heavier elements like oxygen or carbon appear in the escape flow, the stripping has penetrated deeper atmospheric layers. HD 189733b shows both hydrogen and heavier elements escaping. This means the stellar wind strips multiple atmospheric layers simultaneously. The planet isn't just losing its outermost gases, it's losing material from throughout its atmosphere. But stellar wind represents only one of several death mechanisms acting on these planets simultaneously. One side of WASP 18b measures 2,700 degrees Celsius. The other side sits at 1,700 degrees. That 1,000-degree temperature difference exists across a distance you could drive in a few hours if solid ground existed. The gradient is steep, brutal, impossible to survive. This temperature variation creates atmospheric violence beyond comprehension. Hot gas expands and rises on the day side. Cold, denser gas sinks on the night side. The pressure difference drives winds at several kilometers per second. These winds attempt to balance temperature but never succeed. The energy input from the star overwhelms atmospheric circulation's ability to distribute heat evenly. The transition zone between hemispheres becomes a battleground. Hot winds from the day side collide with cold winds from the night side. The collision creates standing shock waves, permanent atmospheric features where gas compresses and heats from the collision energy alone. Temperature spikes locally even higher than surrounding areas. Materials experience thermal stress that would destroy any solid object. Imagine a rock sitting at the terminator. One side faces the day side, heating to 1,000 degrees. The other side faces the night side, cooling to 500 degrees. The temperature gradient across a single rock creates expansion on one side and contraction on the other simultaneously. The rock shatters from internal stress. This thermal cycling might explain why some planets show unexpected atmospheric compositions. Materials break apart under temperature stress. Chemical bonds that stay stable at constant temperature fail when temperature oscillates. Repeated heating and cooling cycles could generate unusual molecules through stress-driven chemistry. The 1,000-degree temperature swings also affect cloud formation patterns. Clouds condense where temperature drops below condensation points for various compounds. On the night side, multiple compounds can condense. On the day side, only the most refractory materials stay condensed. The cloud deck exists in completely different states on different hemispheres. Scientists use these temperature differences to study atmospheric circulation. By measuring how temperature varies across the planet's surface, they can infer wind patterns and circulation cell structures. The data reveals complex, multi-layered circulation systems with different patterns at different altitudes. At high altitudes, winds move in one direction. At mid-levels, they reverse. At low levels near the surface, they move in yet another direction. This three-dimensional circulation creates atmospheric turbulence that mixes materials vertically and horizontally continuously. The mixing affects chemical composition at different altitudes. Molecules created at the surface get carried to high altitudes where they undergo photochemistry. The products of that photochemistry sink back down where heat breaks them apart again. This creates chemical cycles where materials transform repeatedly as they circulate through different atmospheric layers. Temperature variation also drives electrical effects. Hot, ionized gas on the day side contains free electrons and ions. Cooler gas on the night side remains mostly neutral. When these regions connect through atmospheric circulation, electrical currents can flow. The planet might generate its own electrical fields, and lightning through temperature-driven charge separation. Lightning on WASP 18b would be spectacular beyond Earth standards. The energy available from the temperature gradients and the scale of the atmospheric circulation would create lightning bolts spanning thousands of kilometers, carrying currents that would vaporize anything they struck. No instrument has directly detected exoplanet lightning yet, but the conditions on ultra-hot Jupiters make its existence nearly certain. The same physics that creates lightning on Earth applies here, just amplified by factors of thousands due to the extreme environment. The temperature extremes also affect how we observe these planets. Hot regions emit strongly in infrared wavelengths. Cool regions emit less. By measuring infrared emission at different orbital phases, scientists can map temperature across the planet's surface. This technique, called phase curve analysis, reveals detailed temperature maps impossible to obtain any other way. These maps show features beyond simple day-night temperature differences. They reveal hotspots offset from the substellar point, the location directly under the star. This offset indicates strong atmospheric winds carrying heat eastward or westward from where stellar radiation hits hardest. The offset amount tells scientists wind speed. Larger offsets mean faster winds. The patterns reveal atmospheric dynamics in action, showing how exoplanet atmospheres respond to extreme heating in real time. Yet, temperature variations pale compared to the chemistry they enable. WASP 121b creates molecules that should not exist. Titanium oxide appears in its upper atmosphere, despite temperatures hot enough to break it apart. The molecule forms when titanium and oxygen combine. At 3000 degrees Celsius, this bond should shatter immediately. Yet spectroscopic data shows titanium oxide signatures clearly. The molecule persists through constant regeneration. As fast as heat destroys it, atmospheric chemistry creates new molecules. Titanium atoms and oxygen atoms collide with sufficient energy to bond despite the extreme temperature. The collision rate is so high that steady-state concentrations build up. This violates standard chemical equilibrium predictions. Equilibrium calculations say titanium oxide cannot exist at these temperatures. The calculations are based on solid thermodynamics and quantum mechanics. They should be correct, yet observation proves them wrong. Scientists have proposed several explanations. Perhaps local temperature variations create pockets where titanium oxide can survive momentarily before destruction. Perhaps pressure effects stabilize the molecule beyond expectations. Perhaps quantum mechanical effects we don't fully understand allow the bond to persist under conditions theory says are impossible. Another explanation involves photochemistry operating in unexpected ways. Ultraviolet radiation might not just break molecules apart. Under certain conditions, it might help create them. High-energy photons could provide the activation energy needed for titanium and oxygen to bond even in extreme heat. Whatever the mechanism, WASP 121b demonstrates that extreme conditions enable chemistry we cannot replicate in laboratories. Our experiments occur at terrestrial pressures and reasonable temperatures. Exoplanet atmospheres operate at pressures thousands of times higher and temperatures thousands of degrees hotter. Chemistry behaves differently there. Other forbidden molecules appear on different planets. Vanadium oxide shows up where it shouldn't. Complex carbon compounds exist at temperatures that should reduce them to atomic carbon. Methane appears alongside carbon monoxide, both present when thermodynamics says only one should survive. Each detection forces revisions to chemical models. Scientists must add new reaction pathways, adjust rate constants, and account for effects they previously ignored. The models grow more complex trying to match observations, but complexity doesn't always help. Sometimes the observations simply reveal that our understanding has fundamental gaps. We built our chemical knowledge from studying Earth and laboratory conditions. Extending that knowledge to utterly foreign environments produces failures. The forbidden molecules also affect planetary energy balance. Titanium oxide absorbs stellar radiation strongly. Its presence in the upper atmosphere creates heating from within. This drives temperature inversions and affects atmospheric stability. The molecule's existence changes how the entire atmosphere works. Scientists now search for these molecules intentionally. Their presence serves as a tracer for extreme conditions. Finding titanium oxide tells researchers immediately that temperature and pressure have reached levels where standard chemistry breaks down. It marks planets worthy of detailed study. The molecules might also affect habitability assessments. If we detect molecules on a planet that shouldn't exist according to our models, we need to reconsider what else might be possible there. Maybe chemistry allows processes we think are impossible. Maybe life could use biochemistry we consider forbidden. This doesn't mean life exists on WASP 121b. The temperature alone prevents that. But it means our predictions about what chemistry allows under different conditions need humility. The universe consistently shows us chemistry we didn't predict. It might show us biology we don't expect. The forbidden molecules remind us that nature doesn't follow our models. Our models try to follow nature. When they fail, we learn. Each failed prediction is an opportunity to improve our understanding. And the energy levels driving this impossible chemistry reach incomprehensible extremes on the most irradiated worlds ever found. Kelt 9b receives 100,000 times more radiation than Earth. Stop and consider that number. 100,000 times. The star pours energy onto this planet at a rate that defies human-scale intuition. Every square meter of surface receives energy equivalent to having thousands of industrial furnaces pointed at it simultaneously and continuously. This radiation doesn't just heat the planet, it ionizes the atmosphere, stripping electrons from atoms and creating plasma. It drives photochemical reactions at rates billions of times faster than on Earth. It physically pushes on the atmosphere through radiation pressure, adding to atmospheric escape driven by other mechanisms. The radiation spectrum matters as much as the total energy. Kelt 9's star burns blue-white, emitting most of its energy in ultraviolet wavelengths. Ultraviolet photons carry more energy than visible or infrared light. They penetrate deeper into atmospheres. They break molecular bonds more efficiently. Each ultraviolet photon striking an atmospheric molecule can shatter it into constituent atoms. The broken pieces can then react with other atoms to form new molecules. But before those new molecules stabilize, more ultraviolet photons hit them and break them apart again. The atmosphere exists in constant chemical chaos. This level of radiation also affects atomic structure directly. High-energy photons can excite electrons to extreme energy levels. They can knock electrons completely free from atoms through photoionization. The atmosphere becomes partially ionized, containing a mix of neutral atoms, ions, and free electrons. The ionization creates electrical conductivity. The atmosphere can carry electrical currents. Magnetic fields threading through the atmosphere can drive those currents into complex patterns. The interaction between radiation, ionization, magnetic fields, and atmospheric circulation creates physics too complex to model accurately. Scientists trying to understand Kelt 9b must account for processes that don't occur in Earth's atmosphere at all. Standard atmospheric physics equations don't include terms for radiation pressure or plasma dynamics. New equations are needed. New computational approaches must be developed. The radiation levels also mean the planet cannot cool efficiently. Cooling requires radiating energy into space as infrared light. But the incoming radiation overwhelms outgoing radiation by huge factors. The planet accumulates energy faster than it can radiate it away. Temperature climbs until some equilibrium is reached where extreme heat drives atmospheric escape fast enough to carry away excess energy. This energy transport through atmospheric loss represents a cooling mechanism Earth never experiences. On our planet, radiation balance alone determines temperature. On Kelt 9b, mass loss becomes part of the energy budget. The planet cools itself partially by throwing atmosphere into space. The extreme radiation raises questions about planetary formation. How did Kelt 9b end up in such a hostile orbit? Did it form there? If so, how did it accumulate gas against such intense radiation? Or did it form farther out and migrate inward later? If migration occurred, what stopped it from spiraling all the way into the star? These questions extend to planetary populations generally. We observe many planets receiving extreme radiation. This suggests that either planet formation in such locations is common, or planetary migration commonly delivers planets to hostile orbits. Either answer has profound implications for understanding how planetary systems evolve. The survival of planets like Kelt 9b also indicates limits to radiation-driven destruction. Despite receiving 100,000 times Earth's radiation, the planet persists. It loses atmosphere but hasn't been destroyed entirely. This means radiation alone cannot prevent planet formation or immediately destroy planets placed in extreme orbits. But survival comes at a cost. Kelt 9b exists in a state of continuous crisis, constantly losing mass, constantly absorbing energy. It cannot fully radiate, constantly existing on the edge of complete atmospheric loss. It survives, but barely, and some planets face not just extreme radiation, but also internal heat that tears them apart from within. Io orbits Jupiter with volcanic eruptions visible from Earth. Now imagine that on planetary steroids. James Webb detected infrared signatures on K2 141b, consistent with active volcanism, covering the entire surface, not occasional eruptions, not scattered volcanic fields. The entire day side appears to be one massive volcanic system continuously venting material from the interior. The volcanism comes from tidal heating. The planet orbits extremely close to its star. Tidal forces from the star pull harder on the near side than the far side. This difference creates a bulge in the planet's shape. As the planet rotates, different parts of the interior move through the bulge. This movement generates friction. Friction creates heat. On Io, tidal heating from Jupiter generates enough energy to drive hundreds of active volcanoes. K2 141b receives far more intense tidal forces. The heating should be correspondingly more extreme. The planet's interior might be partially or completely molten, churning like the inside of a lava lamp on incomprehensible scale. This molten interior needs somewhere to release pressure. Volcanic vents cover the surface, constantly erupting magma from below. The magma doesn't cool and solidify like on Earth. Surface temperature already exceeds rock melting points. The erupted material flows across the surface as part of the lava ocean. But volcanism does more than just add to surface lava. It releases gases: carbon dioxide, sulfur dioxide, water vapor if any water remains in the interior, various metal vapors. These gases erupt with tremendous pressure, shooting into the atmosphere like volcanic jets. The volcanic outgassing might be the only thing maintaining the atmosphere. Without continuous gas input from volcanism, atmospheric escape would strip everything away. The planet balances on a knife edge, where volcanic input exactly matches escape loss. The atmosphere persists in steady state maintained by this balance. Other planets show similar volcanic signatures. 55 Cancri E displays infrared emissions varying over time, consistent with volcanic activity changing in intensity. The variations suggest eruption cycles, periods of high activity followed by relative calm. These volcanic cycles could affect atmospheric composition. During high activity periods, outgassing increases, atmospheric density rises, cloud formation accelerates. During low activity periods, escape dominates over input, atmospheric density drops, clouds dissipate. The planet's appearance changes with volcanic activity levels. Scientists can potentially use these variations to study planetary interiors. The volcanic output depends on interior composition, temperature, and pressure. By measuring what gases erupt and at what rates, researchers can infer properties of the deep interior impossible to observe directly. The volcanism also affects surface geology in unique ways. On Earth, volcanic eruptions create new land. Lava flows cool and solidify into rock. Over time, volcanic activity builds mountains and island chains. On planets with lava oceans, volcanic eruptions don't create new land. They just add more material to the existing magma sea. This means volcanic planets might show no visible surface features at all. No mountains, no valleys, no impact craters. Just smooth, molten surface, constantly refreshed by volcanic input and atmospheric circulation. Geological history gets erased continuously as everything melts and mixes. Yet the lack of surface features creates its own kind of record. If a planet shows a completely smooth, featureless surface, that tells scientists the surface is liquid or continuously refreshed. It reveals active geological processes, even though no static features exist to study. The volcanic activity also complicates spectroscopic observations. Volcanic gases contain many different compounds. Each compound contributes spectral lines. The combined spectrum becomes crowded with features difficult to disentangle. Scientists must carefully model all possible volcanic outputs to understand what they're seeing. But volcanic hellscapes might actually be prolonging these planets' lives rather than destroying them. GJ 9827d is evaporating so fast it will lose its entire atmosphere in 10 million years. 10 million years sounds long. In human terms, it is. In geological terms, it's a blink. This planet is dying on timescales short enough that we can watch meaningful changes occur during a human lifetime if we had precise enough measurements. The atmospheric escape rate calculation comes from measuring the density of escaping hydrogen. Scientists observe how much starlight gets absorbed by the extended hydrogen cloud surrounding the planet. More absorption means higher density. Higher density combined with measured escape velocities gives the mass loss rate. For GJ 9827d, the numbers indicate approximately 10,000 tons per second, leaving the planet permanently. That's roughly the weight of the Eiffel Tower escaping into space every second, day after day, year after year. The planet cannot sustain this loss indefinitely. Current models predict GJ 9827d will transition from a mini Neptune with substantial atmosphere to a bare rocky planet within 10 million years. The transformation happens fast enough that if we could monitor the planet continuously with precise instruments, we might detect measurable changes in atmospheric density within decades. This discovery reveals that planet populations are not static. We observe planets at different stages of evolution. Some are young and stable, others are dying rapidly. The variety we see in exoplanet populations partly reflects this evolutionary progression. GJ 9827d sits at a critical transition point. It currently has atmosphere, but is losing it quickly. In astronomical terms, we caught it at exactly the right moment to watch the transformation. A few million years earlier, and it would look like a stable mini Neptune. A few million years later, and it would appear as a bare rock. We're seeing it mid-transition. Other planets show similarly rapid evolution. Kepler 1520b orbits so close to its star that it will likely be completely destroyed within a few million years. Not just atmosphere loss, total planetary destruction as the star's gravity tears it apart and consumes it. These rapid evolution timescales change how we interpret planet observations. A planet we observe today might look completely different 10 million years from now. We're not seeing permanent configurations. We're seeing snapshots of temporary states. This has implications for habitability searches. A planet might pass through a habitable phase lasting only a few million years before atmospheric escape destroys it. If we observe during that brief window, we might find life. If we observe before or after, we find a dead world. Timing matters enormously. The rapid evolution also affects statistical studies. When we measure how many planets exist in certain size ranges or orbital configurations, we're measuring current populations. But those populations are changing. Planets are migrating, losing atmosphere, getting destroyed. The distribution we see today differs from the distribution 10 million years ago or 10 million years in the future. Scientists are beginning to incorporate evolutionary timescales into population models. Instead of treating all planets as static, the models now account for atmospheric loss, orbital decay, and other time-dependent processes. This creates a more dynamic picture of how planetary systems change. GJ 9827d provides a test case for these models. The predictions are specific and testable. If the planet still has substantial atmosphere 10 million years from now, the models are wrong. If it becomes a bare rock as predicted, the models are validated. Future observations will tell us which outcome occurs. The countdown to death also raises philosophical questions. How many planets like GJ 9827d have already died? How many formerly habitable worlds now orbit as lifeless rocks because atmospheric escape destroyed them? The galaxy might be littered with planetary corpses, dead worlds that once had atmospheres and possibly even life. We can't resurrect those dead worlds, but studying planets in the process of dying helps us understand how planetary death occurs. This knowledge protects Earth. By understanding what kills exoplanet atmospheres, we better appreciate the processes that could potentially harm our own atmosphere. And sometimes those fatal processes come from gravity twisting entire planets into shapes that physics barely allows. WASP 12b is egg-shaped. This isn't speculation or artistic interpretation. Measurements of the planet's light curve show it reflects more light when presenting its long axis toward Earth and less light when presenting its short axis. The planet is elongated, stretched by gravity into a football shape. The distortion comes from tidal forces. The star pulls harder on the planet's near side than its far side because the near side is closer. This differential force stretches the planet along the star-planet axis. If the planet were made of water, it would bulge easily. But even rocky or gaseous material deforms under sufficient tidal stress. The amount of distortion reveals the planet's internal structure. A rigid, solid planet would resist deformation. An ocean world or gas giant deforms more easily. By measuring how much WASP 12b stretches, scientists infer that its interior is fluid or partially fluid, not solid throughout. The tidal distortion affects the planet's gravity field. Normally, a spherical planet creates a symmetric gravity field. An egg-shaped planet creates an asymmetric field. This asymmetry affects how gas distributes in the atmosphere. Material accumulates preferentially at certain locations, creating permanent atmospheric features. The distortion also affects orbital dynamics. An elongated planet interacts differently with its star than a spherical one. The tidal bulge creates torque that can change the planet's orbit over time. For WASP 12b, calculations suggest the orbit is slowly decaying. The planet spirals inward toward its star. This spiral happens slowly by human standards, but fast astronomically. Observations over the past decade detected measurable changes in orbital period. WASP 12b orbits slightly faster now than it did 10 years ago. The acceleration continues. Eventually, the planet will get torn apart or consumed by its star. The timing of destruction remains uncertain. Current estimates suggest anywhere from 1 to 10 million years before the planet reaches its end. The wide range reflects uncertainty in tidal physics. We can measure the current distortion and orbital decay rate accurately. Predicting future evolution requires models that might be missing important effects. Other planets show tidal distortion to varying degrees. WASP 103b appears more elongated than WASP 12b. WASP 18b shows moderate distortion. The variation depends on orbital distance, planet composition, and stellar properties. Each planet provides a test of tidal theory under different conditions. The distortion creates internal stresses. Imagine being stretched constantly in one direction. Your body would experience strain. Bones and organs would shift position. Pain would be constant. For a planet, the strain manifests as internal friction and heating. This tidal heating adds to the already extreme temperatures from stellar radiation. Some tidally distorted planets might be hotter inside than surface measurements suggest. The heat comes from within, generated by gravitational torture rather than external radiation. The heating can drive geological activity. On Io, Tidal heating from Jupiter creates the most volcanically active body in the solar system. Tidally distorted exoplanets might show similar volcanic intensity amplified by their more extreme environments. Scientists also detect material streaming away from WASP 12b. The planet doesn't just deform, it loses mass. The tidal forces are literally pulling it apart atom by atom. Material from the outer layers escapes through Lagrange points, where stellar and planetary gravity balance. This material forms streams flowing toward the star. Observations reveal these streams through spectroscopy. As material crosses between the planet and star, it absorbs starlight at specific wavelengths. The absorption signatures move over time as the material orbits. Scientists can track individual streams and measure their composition. The composition reveals what layers of the planet are being stripped away. Hydrogen and helium indicate outer atmosphere. Heavier elements suggest deeper layers are being reached. WASP 12b shows heavy element signatures, meaning the stripping has progressed beyond just the lightest gases. This progressive destruction provides a window into planetary interiors. As layers get peeled away, we see material from deeper levels. It's like dissecting the planet through tidal forces. Each layer removed reveals the composition and structure of what lies beneath. But tidal distortion is merely one method the universe uses to reveal planetary interiors. Another involves something simpler, yet equally revealing: the way planets reflect light. The light reflected from HD 219134b reveals minerals that should not exist on planetary surfaces. This rocky super-Earth orbits extremely close to its star. Surface temperature exceeds 700 degrees Celsius. At this temperature, most common minerals melt or vaporize. Yet, spectroscopic analysis of reflected light shows signatures consistent with solid surface material. The minerals must be refractory, compounds with extremely high melting points. Calcium aluminum inclusions, materials found in primitive meteorites, can survive these temperatures. So can certain forms of carbon, tungsten compounds, and exotic oxides that form only under extreme heat. The reflected light spectrum contains features that match tungsten or similar high-temperature metals. This suggests the surface might be covered in metallic deposits, not pure metal sheets. Rather, mineral combinations incorporating tungsten, osmium, or other refractory metals into their crystal structures. These minerals tell a story about planetary formation. They formed in the hottest parts of the protoplanetary disk, close to the forming star where only the most heat-resistant materials could condense. The planet accreted from these exotic materials rather than the rock and ice that built Earth. This challenges the concept of planets as scaled-up versions of familiar rocks. HD 219134b might have surface geology unlike anything in our solar system. Minerals that exist only as laboratory curiosities on Earth could dominate entire continents there. The reflected light also shows variation across the surface. Different regions reflect different wavelengths more or less strongly. This indicates compositional variation. Some areas might be rich in one mineral, while other areas contain different compositions. On Earth, compositional variation comes from geological processes. Plate tectonics concentrate certain minerals in certain locations. Volcanic activity brings different materials to the surface. Weathering and erosion sort materials by density and solubility. HD 219134b lacks these processes. Its surface is too hot for water-based weathering. Tectonic activity seems unlikely given the extreme temperature. Yet compositional variation exists. This suggests formation processes created the variation directly. Perhaps different parts of the protoplanetary disk had different compositions. As the planet swept up material during formation, it incorporated these compositional differences into its structure. Or perhaps impacts created the variation. Large impacts can excavate deep beneath the surface, bringing up material from different layers. The impact sites would show different compositions than surrounding areas. If HD 219134b experienced heavy bombardment, impact scars might create the observed variation. Another planet, 55 Cancri E, shows similar exotic mineral signatures with additional mysteries. Its reflected light varies over time. Sometimes the planet appears more reflective, other times it dims. These variations occur on timescales of hours to days. Scientists proposed volcanic activity as the cause. Eruptions release fresh lava that has different reflective properties than cooled surface material. As eruption intensity varies, surface coverage of fresh versus old lava changes. This changes overall reflectivity, but other explanations are possible. Perhaps the surface melts and solidifies in cycles as the planet rotates. Molten material reflects differently than solid. If parts of the surface cycle between molten and solid states, reflectivity would vary accordingly. The variations provide clues about surface processes. On Earth, observing how surfaces change over time reveals weather, seasons, volcanic activity, and other dynamic processes. On exoplanets, we can't see surface details directly, but monitoring changes in reflected light reveals that surfaces are active and changing. This activity matters for understanding planetary evolution. Static surfaces preserve records of ancient impacts and geological history. Active surfaces erase that history continuously. The difference affects what we can learn about the planet's past. The exotic minerals also affect how we search for potentially habitable planets. We built our concept of habitability around Earth-like compositions: rock, water, carbon-based chemistry. But if planets can be made of entirely different materials, maybe habitability requires rethinking. Life as we know it depends on specific chemistry. That chemistry requires certain elemental building blocks and environmental conditions. A planet made of refractory minerals and lacking water cannot host Earth-like biology. But could different biochemistry evolve based on different minerals under different conditions? These questions remain speculative, but the exotic mineral planets force us to ask them. They prove planets need not resemble Earth. They can be made of entirely different stuff operating under completely different rules. And above some of these exotic surfaces, the sky itself becomes poisoned with compounds that make Earth's worst pollution look pristine. GJ 1214. B has an atmosphere so hazy that starlight barely penetrates. This super-Earth orbits a red dwarf star at a comfortable distance where temperature should allow water to exist. Instead of clear skies, observations reveal thick hazes blocking optical light almost completely. Only by observing in infrared wavelengths can scientists see through the murk. The hazes form through photochemistry. Ultraviolet radiation from the star breaks apart atmospheric molecules. The fragments recombine into complex compounds that don't exist in Earth's atmosphere. These compounds condense into tiny particles suspended in the air. Millions of particles per cubic centimeter create a dense fog. On Earth, photochemical smog forms over polluted cities when sunlight reacts with vehicle emissions. The smog appears as brown haze, reducing visibility. GJ 1214b's photochemical hazes are similar in principle, but vastly more extreme. The entire atmosphere is smog. Visibility would be measured in meters, not kilometers. The haze particles affect atmospheric temperature structure. They absorb some stellar radiation and scatter the rest. This heating and scattering changes how energy flows through the atmosphere. Temperature doesn't decrease smoothly with altitude, as it would in a clear atmosphere. Instead, temperature profiles become complex, with warm and cool layers intermixed. The hazes also affect habitability. If GJ 1214b has a surface ocean, the hazes would block sunlight from reaching it. Photosynthesis would be impossible. Any life in the ocean would need to rely on chemical energy rather than solar energy. This limits biological complexity and productivity dramatically. Scientists debate the composition of GJ 1214b's hazes. One hypothesis suggests hydrocarbon particles similar to Titan's atmosphere. Methane molecules get broken by ultraviolet light. The carbon and hydrogen atoms recombine into ethane, propane, and more complex hydrocarbons. Eventually, these hydrocarbons form particles that create the observed haze. Another hypothesis proposes water-based hazes. If the atmosphere is rich in water vapor, ultraviolet radiation can break water molecules into hydrogen and oxygen. The oxygen might combine with other elements to form clouds of various oxides. These clouds would create haze, similar to what's observed. A third possibility involves sulfur compounds. If volcanic activity releases sulfur dioxide, photochemistry can convert it into sulfuric acid droplets. Sulfuric acid clouds create Venus's thick hazes. Similar processes might operate on GJ 1214b. Distinguishing between these scenarios requires detailed spectroscopy at multiple wavelengths. Each compound absorbs and scatters light differently. By carefully measuring the spectrum of light passing through the atmosphere, scientists can identify which compounds are present. But the hazes make this difficult. They scatter light so effectively that spectral features get washed out. The atmosphere appears featureless in some observations. Scientists call this a flat spectrum. It provides little information about composition beyond confirming that hazes exist. New observational techniques help penetrate the hazes. By observing at infrared wavelengths, where hazes scatter less effectively, James Webb can see deeper into the atmosphere. The data reveals the structure and composition hidden beneath the photochemical smog. Other planets show different types of hazes. Kepler 5.1b has such extensive haze layers that the planet appears vastly larger than its actual size. The hazes extend hundreds of kilometers above the solid or liquid surface. The planet looks like a puffball, light and diffuse. These extended hazes form when gravity is relatively weak and atmospheric temperature is high. The combination allows haze particles to rise to extreme altitudes before settling. The atmosphere develops a thick, fluffy structure unlike anything in our solar system. The hazes affect how these planets lose atmosphere. Particles can trap escaping gases, slowing atmospheric escape, or they can enhance escape by absorbing radiation and transferring energy to gas molecules. The net effect depends on haze, altitude, composition, and particle size. Understanding photochemical hazes matters for characterizing exoplanet atmospheres. Many potentially habitable planets might be shrouded in hazes. Without accounting for haze effects, we might misinterpret atmospheric spectra and reach wrong conclusions about habitability or composition. Yet some atmospheres contain not just hazes but gases that suggest something even more disturbing might be happening beneath the smog. K-18b shows dimethyl sulfide in its atmosphere. On Earth, only living organisms produce this gas. The detection sent waves through the astrobiology community. Dimethyl sulfide is considered a potential biosignature, a gas that indicates life's presence. Finding it on K-18b, a planet in its star's habitable zone where liquid water could exist, seemed like exactly what scientists hoped to discover. Then the problems emerged. K-18b orbits a red dwarf star. The planet receives intense ultraviolet radiation, especially during stellar flares. This radiation could drive photochemistry that produces dimethyl sulfide through abiotic processes. No life required, just chemistry acting under extreme radiation conditions. The planet also experiences tidal heating from its close orbit. This heating could drive volcanic activity. Some volcanic systems on Earth release sulfur compounds. If K-18b has similar volcanism operating at larger scales, it might produce enough sulfur-containing gases to create dimethyl sulfide through atmospheric chemistry. Another possibility involves meteorite impacts. Impacts can deliver both sulfur and organic compounds. Under the right conditions, impact-delivered materials might react to form dimethyl sulfide. If K2-18b experiences heavy bombardment, impacts could maintain steady concentrations of this supposed biosignature gas. The dimethyl sulfide detection itself remains uncertain. The spectral feature is subtle, close to the detection limit. Different analysis methods give slightly different results. Some scientists believe the signal is real. Others think it might be instrumental noise or contamination from other atmospheric compounds. This uncertainty highlights a critical problem in biosignature detection. We need definitive proof before claiming life exists elsewhere. A single, ambiguous spectral line is not enough. We need multiple independent biosignatures, all pointing to the same conclusion. K2-18b also shows methane and carbon dioxide in its atmosphere. On Earth, methane is produced biologically by microbes, but methane has many abiotic sources too: volcanic outgassing, geological reactions, photochemistry. Without additional context, methane proves nothing about life. The combination of gases matters more than any single gas. If we detected oxygen, ozone, methane, and nitrous oxide together at concentrations far from chemical equilibrium, that combination would be much stronger evidence for life. Earth's atmosphere has exactly this combination. Life maintains it. K2-18b doesn't show this combination. It shows gases that could be explained by non-biological processes. The atmosphere might be completely dead despite containing a supposed biosignature. This teaches an important lesson. We must be extremely cautious claiming biosignature detections. The universe is complex. Chemistry under extreme conditions can produce unexpected results. What looks like biology might just be exotic chemistry we don't understand yet. Other planets show similar false biosignatures. Some have oxygen in their atmospheres. On Earth, oxygen comes from photosynthesis, but oxygen can be produced abiotically through water photolysis. Ultraviolet radiation splits water molecules. Hydrogen escapes to space. Oxygen accumulates. Venus has phosphine in its atmosphere, another supposed biosignature. Some scientists claim this proved life in Venus's clouds. Others explained it through abiotic volcanic chemistry or photochemistry. The debate continues with no clear resolution. These false alarms frustrate the search for life, but also refine it. Each false biosignature teaches us what to look for and what to dismiss. We learn which gases truly require biology and which have abiotic explanations. The field matures through these challenges. The real test will come when we find a planet showing multiple robust biosignatures that cannot be explained abiotically. A planet with oxygen and methane coexisting far from equilibrium. A planet with seasonal variations in atmospheric gases consistent with biological cycles. A planet showing spectral features matching chlorophyll or other biological pigments. K2-18b isn't that planet. Its gases can be explained without invoking life, but the search continues. James Webb and future telescopes will examine hundreds more potentially habitable worlds. Eventually, we might find the combination of signatures that proves life exists beyond Earth, or we might not. Which brings us to the most unsettling realization these extreme planets force upon us. Every disturbing planet James Webb discovers makes Earth look more like a miracle. We've explored worlds where glass falls sideways at supersonic speeds, planets hot enough to vaporize rock, atmospheres collapsing in real time, worlds evaporating into space, lava oceans, metal clouds, photochemical smogs thick enough to block all light, gravity stretching planets into egg shapes. None of these planets could host life as we know it. Temperature alone kills any possibility on most of them. The ones with moderate temperatures face other deadly problems: extreme radiation, atmospheric escape, tidal locking creating frozen night sides, hazes blocking sunlight, toxic atmospheric chemistry. The sheer number of ways planets can be hostile is staggering. For every parameter that must be right for habitability, there are dozens of ways it can go wrong. Too close to the star means incineration. Too far means freezing. The wrong stellar type means deadly flares or insufficient light. The wrong planetary mass means crushing gravity or atmosphere loss. Statistical studies of exoplanet populations reveal uncomfortable truths. Most planets orbit in configurations hostile to life. Most orbit red dwarf stars prone to flares. Most orbit closer than Mercury orbits our star. Most are either too hot or too cold for liquid water. Even planets in nominal habitable zones face challenges. Many are tidally locked. Many experience atmospheric escape. Many receive intense stellar activity during their star's youth. The habitable zone defines where water could exist in theory. It doesn't guarantee habitability in practice. Earth sits in the habitable zone around a stable, middle-aged, sun-like star. We have a large moon stabilizing our axial tilt. We have plate tectonics, recycling carbon, and regulating climate. We have a magnetic field protecting our atmosphere from stellar wind. We have Jupiter deflecting some dangerous asteroids. Each of these factors contributes to long-term stability. How many planets have all these factors? Current estimates suggest Earth-like planets might be rare, not impossibly rare. The galaxy contains hundreds of billions of stars. Even if only 1 in a million has an Earth-like planet, that still leaves hundreds of thousands of such worlds. But those worlds are scattered across a galaxy 100,000 light-years wide. The nearest might be dozens or hundreds of light-years away. Distance becomes a barrier nearly as absolute as the conditions that kill habitability. The extreme planets also teach us that planetary systems evolve in chaotic ways. Planets migrate, they lose atmospheres, they get captured into deadly orbits. A planet might start in a habitable configuration and end up uninhabitable through no fault of its own, just bad luck in gravitational interactions. This raises the disturbing possibility that habitable planets might be temporary. A world could be habitable for 1 billion years, then lose everything to atmospheric escape or orbital migration. If habitable conditions last only briefly on cosmic timescales, the number of currently habitable worlds might be far less than the number of worlds that were ever habitable. For civilization and intelligence to develop, habitability must persist for billions of years. Earth needed 4 billion years to evolve complex life and intelligence. If most habitable periods last only millions of years, intelligent life cannot develop even if simple life does. The extreme planets we observe might be failed Earth-like worlds, planets that started with atmospheres and moderate temperatures but couldn't maintain them. Dead worlds that once had potential but lost it to stellar activity, atmospheric escape, or orbital decay. We cannot know which planets in the galaxy are currently habitable without visiting them or observing them in detail. Distance and technological limitations prevent that for now. But the extreme planets James Webb reveals tell us that most worlds fail the habitability test. They fail spectacularly, in ways that make survival impossible. This makes Earth's habitability more precious. We exist on a world that passed every test. It formed at the right distance. It retained its atmosphere. It avoided extreme impacts. It developed a biosphere that regulated climate. It remained stable long enough for intelligence to evolve. The odds against this seem astronomical, yet here we are, which suggests either Earth-like conditions are more common than current observations indicate, or we are extraordinarily lucky. And what comes next might answer which interpretation is correct. James Webb has examined fewer than 100 exoplanet atmospheres in detail. Thousands more await. The telescope's instruments can detect chemical signatures from planets dozens of light-years away. Each observation reveals new atmospheric compositions, new temperature structures, new cloud patterns. The variety seems endless. Every planet offers surprises. Future observations will focus on smaller planets. Most discoveries so far involved gas giants because they're easier to study. Large size means strong signals. But smaller rocky planets hold more interest for habitability studies. James Webb can study some of these worlds if they orbit small, dim stars where the planet-to-star size ratio is favorable. Several dozen rocky planets in habitable zones await detailed characterization. These worlds might show water vapor, oxygen, or other indicators of conditions suitable for life, or they might reveal new categories of extreme environments we haven't encountered yet. Scientists predict more exotic chemistry discoveries. The forbidden molecules already detected are probably just the beginning. As observations improve, we'll find atmospheric compositions that violate chemical equilibrium even more dramatically. New reactions will be discovered, new molecular species identified. Chemistry textbooks will need revision. Temperature extremes will likely exceed current records. Kelt 9b holds the heat record now, but hotter planets probably exist. Some might orbit even more luminous stars or circle at tighter orbits. The question is whether planets can survive long enough at such extreme temperatures for us to observe them before they evaporate completely. We'll also discover more planets in the process of dying. Atmospheric escape operates continuously across the galaxy. At any given moment, millions of planets are losing their atmospheres. James Webb can measure escape rates for dozens of these worlds, providing statistics on how common planetary death is. The strangest planets might not be hot worlds. Cold worlds far from their stars could have bizarre icy chemistry. Thick atmospheres of hydrogen and helium might cover ocean worlds, where high-pressure ice forms exotic crystalline structures. These cold giants remain mostly unexplored because they emit little radiation for telescopes to detect. Future missions beyond James Webb will expand capabilities further. NASA's Habitable Worlds Observatory, planned for the late 2030s, will specifically target Earth-like planets. It will have the sensitivity to detect faint biosignatures and resolve atmospheric features impossible to see now. European Space Agency's Ariel mission will launch in the late 2020s to survey exoplanet atmospheres across a wide range of sizes and types. Its broad survey approach will reveal population statistics. How many planets have clouds? How many have hazes? What atmospheric compositions are most common? Ground-based telescopes are also improving. The extremely large telescope under construction in Chile will have a mirror 39 meters across. Its enormous light-gathering power will enable direct imaging of some exoplanets, allowing us to see them as actual points of light rather than indirect signatures. These future observations will answer fundamental questions. How common are Earth-like planets? How many habitable worlds exist in the galaxy? What factors determine whether a planet becomes habitable or extreme? Can life adapt to conditions we currently consider impossible? But some questions might remain unanswered. If the nearest habitable planet lies hundreds of light years away, detailed study might exceed our technological capabilities for centuries. We might confirm thousands of extreme planets while habitable ones remain frustratingly out of reach. The extreme planets will continue to surprise us. Every new observation reveals phenomena we didn't predict. Glass rain, metal clouds, lava oceans, these were unexpected. Future discoveries might be even stranger. Planets with conditions so alien we lack vocabulary to describe them properly. We're in the early days of exoplanet characterization. We've barely scratched the surface of the diversity that exists. The universe has billions of years and trillions of planets to experiment with different configurations. We're sampling a tiny fraction of that vast parameter space. What we learn from extreme planets will inform how we protect Earth. Understanding atmospheric escape helps us appreciate how fragile our own atmosphere is. Studying planets that lost habitability teaches us what to avoid. The extreme worlds serve as laboratories and warnings simultaneously, and that brings us to the question we've been avoiding. If disturbing planets are common, what does that say about finding life? We've examined 30 worlds where existence is torture or impossible. Glass rain, metal clouds, evaporating atmospheres, lava oceans. crushing gravity, lethal radiation, toxic chemistry. Each represents a different way the universe creates hell. These aren't rare exceptions. They're common. Ultra-hot Jupiters number in the hundreds discovered so far. Tidally locked planets probably number in the millions across the galaxy. Atmospheric escape affects countless worlds. The universe mass produces hostile planets. Now, consider the implications for biology. Life requires narrow conditions, moderate temperature, liquid water, stable atmosphere, protection from radiation, chemical building blocks, energy sources, surface or subsurface environments where complexity can develop, time measured in billions of years. Every extreme planet we discover represents a world where those conditions don't exist. Every planet evaporating into space is a planet where life cannot persist. Every lava ocean planet is a location where biochemistry is impossible. Every radiation-blasted world is a place where organic molecules break apart. The sheer number of ways to be uninhabitable vastly exceeds the ways to be habitable. The parameter space of possible planetary conditions is enormous. Only a tiny fraction of that space permits life. Most of the space contains the extreme planets we've explored. Statistical studies suggest that for every Earth-like planet, dozens or hundreds of extreme planets exist. The ratio might be even more skewed. We might inhabit one of the rarest types of worlds in the galaxy. This doesn't mean we're alone. The galaxy contains hundreds of billions of stars. Even if Earth-like planets are rare, large numbers still exist in absolute terms. But it means those planets are scattered across vast distances. The nearest might be far away. It also means the universe is largely hostile to life. Most places cannot support biology. Most planets are dead or dying. The cosmos is not life-friendly by default. It's harsh, extreme, violent. Life exists in small protected pockets within an ocean of inhospitality. The extreme planets force us to confront uncomfortable realities. We are not living on a typical planet. Earth is an outlier, an anomaly. The conditions we enjoy are rare and precious. They might not last forever. Atmospheric escape, stellar evolution, orbital changes, these processes affect all planets eventually. Earth's habitability is temporary on cosmic timescales. This realization should inspire both humility and urgency. Humility because we're not the center of anything. The universe doesn't care about our survival. It creates extreme planets far more readily than habitable ones. We exist despite the universe's general hostility, not because of any special providence. Urgency because habitable conditions are fragile. If we contaminate our atmosphere, destabilize our climate, or destroy our biosphere, we cannot simply move to another planet. The nearest habitable world might be unreachably far. We have one planet, these conditions, this brief window of habitability. The extreme planets also reshape how we search for life. We should focus on planets most unlike the horrors we've examined. Sun-like stars instead of red dwarfs, moderate orbital distances, stable atmospheres, evidence of plate tectonics, protective magnetic fields. Each criterion filters out worlds more likely to be extreme. But we should also remain open to surprises. Life might adapt to conditions we consider impossible. The false biosignatures teach us that chemistry under extreme conditions behaves unexpectedly. Maybe biology can too. Maybe life finds ways to survive in environments that would kill Earth organisms instantly. The ultimate answer to whether we're alone requires continued observation. James Webb has shown us dozens of extreme worlds. Future telescopes will show us hundreds more. Among those hundreds, we might find a few that aren't extreme. A few where conditions permit life, a few where biology might have taken hold, or we might not. We might survey thousands of planets and find only variations on the extreme themes we've already seen. Glass rain on one world, lava oceans on another, metal clouds, toxic hazes, crushing gravity, evaporating atmospheres. a gallery of horrors extending as far as we can see. That outcome would be the most disturbing finding of all. Not that extreme planets exist, we know they do, but that they might be all that exists. That habitability might be so rare that Earth stands nearly alone in a galaxy of dead worlds. We cannot know yet. The data remains incomplete, but every new extreme planet discovery makes that disturbing possibility slightly more plausible. James Webb will keep watching. New worlds will be found, new atmospheres characterized, new extremes discovered. Each observation adds to our understanding of how planets work and what makes them habitable or hostile. The most disturbing planet might still await discovery. Somewhere in the data yet to be collected, a world more extreme than anything we've seen might hide. Temperatures higher than Kelt, 9b. Winds faster than HD, 189733b. Chemistry more impossible than WASP, 121b. Conditions so severe they challenge our concepts of what planets can be. Or perhaps, the most disturbing finding will be discovering that planets like Earth, with blue skies and moderate temperatures and life covering the surface, are so rare that finding another takes centuries of searching. Either way, the universe has shown us its capacity for creating worlds we never imagined. Worlds that shouldn't exist according to our models. Worlds where physics operates at extremes. Worlds where chemistry breaks its own rules. Worlds dying in real time. And among all these disturbing possibilities, one fact remains certain. We exist on the planet that worked. Against the odds, in a universe that produces extreme worlds readily and habitable ones rarely, we inhabit the exception. The question isn't whether disturbing planets are common. They are. The question is what we do with the knowledge that our world is precious because it's so uncommon. The universe has given us our answer through 30 extreme planets. Earth is rare, habitability is fragile, and the cosmos is stranger and more hostile than we ever suspected.